Look at the heavy steel framework of a skyscraper going up. It's easy to assume if one of these massive vertical pillars were to fail, the sheer weight of the building would simply crush it straight down. Long structural members rarely fail through compression alone. Instead, they spring violently outward in the middle. This lateral bending, known as buckling, happens well before the steel itself actually yields or fractures. It occurs when a column reaches a state of unstable equilibrium. Under pressure, the column remains technically balanced, but the slightest physical imperfection in the metal causes the massive vertical load to rapidly amplify into a lateral bend. Once a column reaches a certain length, its material strength stops being the primary defense. Whether it holds the building up or collapses becomes a problem of geometry. To keep a structure standing, engineers must calculate the critical load, the exact mathematical tipping point where compression forces the geometry to buckle. A column's physical height is deceiving. What actually dictates its strength is how it's anchored within the surrounding framework. Engineers measure this using the effective length factor, or the K factor. This mathematical modifier adjusts a column's functional length based on how tightly its ends are restrained. This diagram outlines boundary conditions. The first panel shows a pinned column. Its effective buckling length equals its physical length. Rigidly fixing both ends cuts that length in half. Conversely, leaving one end free doubles the effective length, bowing under half the load. Ultimately, the security of those boundary anchors dictates the column's stability far more than its total physical height. Beyond the outer boundaries, we have to look inward at the column's cross-section. The internal shape of the metal is the next critical variable. A solid steel rod bends easily under pressure, but reorganizing that same metal into a hollow tube, pushing it outward, multiplies its geometric stiffness. We combine effective length and cross-sectional shape into a single metric, the slenderness ratio. For structural steel, a slenderness ratio above 100 places a support in the category of a long column. This graph plots critical stress against the slenderness ratio. Above 100, failure follows Euler's formula. As a column gets thicker and shorter, its ratio drops below 100 into the intermediate zone. Here, columns follow the Johnson parabola, accounting for both bending and material yielding. The slenderness ratio serves as the definitive metric, telling an engineer whether the column is fighting the limits of physics or the limits of geometry. In practice, engineers often must support a massive load with a slender column without adding any more weight or material to the structure. The solution is a lateral brace. Pinning the midpoint in place cuts the effective length of the column in half, immediately reducing the slenderness ratio without adding significant weight. This bracing is only effective if it specifically restrains the column along its weakest geometric axes. Under extreme compression, a structural member seeks the path of least resistance, bowing in the direction where its cross-section is the narrowest. Even with optimized geometry, real-world construction has flaws. To compensate for these imperfections, engineers apply a factor of safety, slashing the calculated critical load to a safe working limit. Steel's inherent strength is only half the story. Skyscraper stability relies on the precise choreography of end constraints, lateral bracing, and cross-sectional geometry to keep the threat of buckling at bay.